Good morning, students. We are now familiar with how to calculate work when the force is constant. Until now we discussed when the force is constant, if the body undergoes displacement in the direction of force, then how to calculate work done. Work done is equal to force into displacement, that is dot product of force vector and displacement vector. But in case if the force is variable, then how to calculate work done? Most of the cases force will be changing. Force will be always variable force. Gravitational force, magnetic force, electrostatic force of repulsion, electrostatic force of attraction. In most of the cases, forces are variable. So how to calculate work in such situation of variable force? That is the task that we are going to do. So let us first discuss how to calculate work when the force is constant with the help of a graph. When force F is constant and body undergoes in the direction of force, body moves from xi to xf. Xi is initial position, xf is a final position. Along the straight line, body moves from xi to xf along straight path. Then if you draw the graph, suppose I am taking displacement along x axis, force along y axis. Suppose this is initial position xi and this is final position xf. Suppose the force at this initial position is some constant force, let it be say 10 Newton. I will write this force as F equal to, let us say, 10 Newton. Then if it is a constant force not changing from xi to xf, not at all changing, then you will get a straight line graph of F versus x. This is displacement, this is force. When constant force is acting, then we will get a straight line because it is not changing at all. Then if I want to calculate work, then by definition, work done we know as F dot D. Here force and displacement are in the same direction. Both are in the same direction and displacement is taking place along the direction of force. Then we know it becomes F into D. But here displacement is xf minus xi, final position minus initial position. Xf minus xi. So what you get from the graph? Let us look at this. So if you take this position of xf, this is the f, and this is the position xi, this is f. So if you draw this outline, you see you will get a rectangle. Call this rectangle as A, B, C, D. Now if I calculate area of this, what do I get? Area of rectangle. Area of rectangle is equal to length into breadth. Breadth, let me take it as AB. AB into AD or AB into BC, both are same. AB into AD. What is AB? AB is the constant force. AB is the constant force. And what is AD? AD is the change in position, xf minus xi. xf minus xi. Is it not giving you the same result? So thus we conclude work done can be calculated as using graph F versus D graph. Using F versus D graph, work done can be calculated as area under the straight line graph. So area under the straight line graph is area of this rectangle, that is area of rectangle in this example. So area of this rectangle thus gives us F into xf minus xi, that is F into delta x we can call, F into delta x, that gives us work done, F into delta x. So the area under the force versus displacement graph, gives us work done. That is how we conclude. Therefore, area under force versus D graph gives the work done. So with this basic knowledge, now we are going to calculate what happens if the force is not constant. If the force is not constant, then you will get a curved graph. Graph will not be straight line at all. Some at point B if it is same value, at another point it will be increased value, at some other point it will be decreased value. So the graph will not be straight line. Then we apply the same concept. We will calculate area under this force versus displacement graph. The total area under the force versus displacement graph gives us the work done. Then how to calculate that area? That becomes the question. If it is a regular surface, if it is a regular geometrical shape, then it is very easy to calculate. If it is a rectangle, if it is a circular, if it is any other regular surface, it is very easy to calculate the area. If it is a irregular graph, then how to calculate area. That is what we are going to see for work done by a variable force. Now let us consider there is a variable force acting on an object. Again the object moves from initial position xi to xf, but during its motion along the same line, along the same direction of applied force, the force is not constant. Suppose if we draw the graph of force versus displacement, we get such a graph. This corresponds to initial position xi and this corresponds to the final position xf. Means if you look at the graph, the force is not constant. If the force would be constant, you would be getting straight line as I had drawn earlier. Now force is initially increasing and reaching some maximum value, then again it is decreasing. In such case, how to calculate the work done? So the idea is to calculate the total area under the graph. So if we calculate the area under the graph, we get the work done by this variable force in changing the position of the object from xi to xf. That's how we are going to calculate. But how to calculate the area? Now there is a procedure. So let us suppose at certain instant, say here, the corresponding force is, let us say, Fx. Fx, let it be the force at this position, and when this acts, the body undergoes at displacement, say, let us say delta x. Let us say displacement delta x. So let us take this displacement as small displacement delta x. Small displacement delta x. For this small displacement delta x, force acting, we assume the force acting to be let us assume the Fx is the constant force for a small displacement delta x. Then we can calculate what is that small amount of work done for a small displacement delta x. Yes. Then area of this strip, area of this rectangular strip gives us the small work done in moving the object through a small displacement delta x for a force Fx. So first I will write, if the force is variable such as force as a function of x. Force as a function of x means from position to position the force is taking different values. Force is a function of position x. Then total area under the F versus D graph, F versus D graph results into work done. This is what we already know. Now we are going to calculate the area under this graph. So for that, let Fx be the constant assumed to be constant force for small displacement delta x. Then work done, small work done, I will write it as small work done. Small work done for this small displacement, I will write it as delta W is equal to F into delta x. So if you take F into delta x, is it not giving you area of this small strip? If you call this A, B, C, D, so it gives you small area. I will write it as delta A. Delta is a small area. Small area of ABCD rectangular strip. So now what I will do, throughout this area under the graph, I will go on making such small displacements. Delta x, delta x, delta x, delta x, delta x, and the delta x. Then the procedure is to calculate area of all these individual stripes. Then add all those individual area. If you add this, let us say 1, 2, 3, 4, 5, 6, 7 areas, then you will get the total area under the graph, right? So the procedure is to divide. Now consider such small displacements delta x as shown, and calculate small works delta w's. Delta W1, let me say for this first displacement, let me call it as delta W1, for second displacement delta W2, and so on for the entire area. Then if you add all these, are you not going to get the total work done? Therefore, total work done from position xi2 to the final position xf for the movement of the body from xi to xf. Total work done can be calculated as W is equal to sum of delta W1 plus delta W2 and so on. So this can be written as, therefore, if you call this one as F1 delta x, F2 delta x, F3 delta x and so on, I will write it as summation of all such delta W's, summation of delta W's starting from xi to final position xf, starting from xi to final position xf. So this gives us total work done. That's finally I can write as xi to xf f delta x, f delta x, because delta W is equal to f delta x. So summation of all such products of force and small displacements give you total work done. But here there is a problem. If you carry out the summation, you will find some shortcoming. Such small areas will be left unaccounted for. Such small areas will not be taken into account. So this will become an approximate calculation. This will be an approximate calculation. So to avoid this approximation, suppose we make these displacements very small. Displacement delta x, if it is tending to be 0, if delta x is made infinitesimally small, dx, and then carry out the same procedure, then the summation will not be now limited to only 7 areas now. It will be going to be unlimited. Summation will be extended from xi to xf for very large number of such small stripes. Then we replace this summation by the symbol called as integration. So there we write, if the displacement are allowed to approach 0, if the displacements are allowed to approach 0, okay? Not exactly 0 but tending to 0. Mathematically we write if delta x is tending to 0, then the number of terms are going to be unlimited. Number of terms in the sum. Number of terms in the sum increases without any limit. Without limit. It increases without limit. But the sum approaches, sum means this entire sum approaches what is known as a definite integral between xi to x. What is the meaning of this sentence? I am going to write mathematically. See, the meaning of this, the number of terms in the sum increases without limit. but the sum approaches a definite integral between xi to xf. That leads to the entire area under the graph. Same graph I have drawn once again. So initially I have taken a strip, small strip here representing delta x. If that delta x is made infinitesimally small, that is what we call as dx. Delta x, limit delta x tending to 0, limit delta x tending to 0 is termed as dx. Then if force for that dx is f and dx is a small displacement, then small infinitesimal small amount of work done is given by dw. dw is equal to f dx. So if you integrate from xi to xf, then we will get the complete area under the graph. So if you calculate in this fashion, you will get the complete shaded graph, the complete shaded region as area under the graph. So if you call this by some terms A, B, C, D, then the meaning of this I am getting total work done, W is equal to limit as delta x tends to 0, limit as delta x tends to 0, summation from xi to xf, f x, f as a function of x, delta x. Same summation, now it is to be replaced by integration. Now the meaning of this is integration. Then w becomes integration. This is the symbol for integration. Integration from initial point xi to final point xf. This is called a lower limit xi and this is called upper limit xf. So this gives us f x, f as a function of x, that is the variable force. Limit delta x tends to 0 as delta x becomes now dx. So this becomes the meaning of the work done by a variable force, where fx is a variable force which is a function of x. So this gives us exact value of total work done in carrying out the body from xi to xf when the force is not constant, when the force is variable force. So this definitely gives us area under the entire area under force versus displacement graph. So that is nothing but area of this irregular surface, area of OA, sorry, not area of AB, area under ABCD, ABCD. So this is the integration. So now onwards we are going to learn the application of integration. I think you got the point now. If it is restricted to delta x, then we use summation of fx delta x, which will be an approximate method. But when this delta x is reduced to infinitesimally small, say, if it is reduced to infinitesimally small, let me draw it very close. Even this closeness is also not that small. So if I call this close displacement as dx, close small infinitesimal small displacement as dx, and force acting for this close small dx is, let us say, f, then small work done dw, small work done for this is going to be f dx. We assume for that small displacement force is constant, then force into displacement gives us small amount of work done. Then throughout this, divide this entire shaded region into such small displacements and go for summation. That is the meaning of integration. Integration, it is called as a definite integral because limits are mentioned here. From where to where? From xi to xi. If we integrate such small work done, then we get total work done. From where to where? From lower limit xi to upper limit xi. So this is the meaning of the work done under variable force. In general, we will learn about what is the meaning of integration and we'll learn some formula. In general, please remember, work done by a variable force is calculated as area under force versus displacement graph. Area under force versus displacement graph. If you remember this guiding principle, area under the force versus displacement graph, if you remember this, then force versus displacement graph, then that will be helpful to solve number of numerical problems. This we will see in the next video with some numerical problems. Thank you. Have a nice day.